Calculator Auto Lab let you do the lab as well. So I added the lab grader to the calculator and microwave assignments, but you don't know what the lab test cases are yet, so you can't really do it. Some of the test cases are so basic that you'll just accidentally get them, and that's fine. I don't care. Um, but the other ones, to actually finish the lab, you'll need the lab on Thursday, which won't be released till Thursday, of course. Yeah, so you can't really do the lab in advance. But like one of the microwave tests is push the popcorn button, and that's it. You're probably just going to test that anyway if you're writing your own tests. Some of the calculator test cases are right from the doc. So if you're taking my examples and coding those as test cases, you're just going to get a couple of the lab ones on accident. That's fine. Yep, this week's. So we're at a point in this course, at least by the end of this week, once everybody's had the homework interviews, that you've seen the structure of how everything's going to work. There aren't really any more surprises after this. Now we can finally digest a bit. You understand the structure of the course, and we can talk about that structure more in depth as we go. Each pre-homework lab is going to be, here are some test cases, code these, preferably review the homework before you start lab, or else you're eating into that 2 hours. And then we're going to give you test cases for each of the objectives, and you got to code up those test cases and submit. The learning objective labs, those Thursday labs, will be like you saw. Here are some programs. Explain to me what happens. The interviews, those are going to be the same. Each homework interview is going to have the same feel. Each learning objective interview is going to have the same feel. So you got an idea of everything that's going to happen in this course. Yeah, right, P. Autolab. That is what I said, right? I uploaded the graders, the versions of the graders that include the labs for those homework assignments. So you're going to get the feedback for the lab, even though lab hasn't started yet. But you will get the feedback in Autolab for all the lab objectives. Yeah, calculator is pretty neat. So a little history behind calculator. I actually took way back when. I actually took 116 with Dr. Alphonse, and he had this calculator assignment. So I did steal it from him, and he actually stole it from somebody else, or borrowed with permission, rather. And I talked to him before I used it. And it was the most notable assignment that I've taken, at least in my early years of education. And I was kind of sad that it went away. He stopped running the assignment, and I was sad about that. So once I took 116, I'm like, calculator's making a comeback, baby. And then I added microwave. I designed that in the same vein as calculator, but just a different application. But this state pattern, it was really eye-opening to me when Dr. Alphonse stood in front of the lecture, back when we were IRL, of course, and he said, you're going to write a calculator. And you're going to write a calculator without using control flow. And I'm like, yeah, right, you can't do that. I didn't believe him at all. And then he started explaining the state pattern, and I'm like, holy crap, we can actually do that. Wow, polymorphism and inheritance are freaking cool. So I really like the assignment personally, and I made sure that I ran it each time I ran this course. Academic integrity alert. You can't just scream something in all caps without... Oh, because I stole the assignment. I see. All right, so let's get into some lecture. And I want to rerun this. Rerun. It should pop up right here. All right. Oh, that's actually kind of annoying. What am I looking at here? It's way over here. Okay. I got this. I got this. And then I can move this. It's new technology. Hold on. We're going to be fancy with this, though. And put the jump wrap right there. I'm going to use that shortly. I just wanted to get it set up. Set up now. All right. So the state pattern, we learned. When is the second homework due? Just check the website, dude. I don't know off the top of my head. I think October 11th, but I'm not sure. So the state pattern, we saw the state pattern on Monday. So you know everything that the state pattern is, but like most things in this course, it comes fast. I throw it out there, and then it's up to you to figure it out. But unlike the topics that we've already discussed, we're going to take 2 more lectures to digest this thing. We're going to look at examples. Today I'm going to show you an existing example from the Physics Engine homework, the jumper game that the Physics Engine was added to. And then on Friday, I'm going to code an example from scratch. We're going to start with just a problem statement, and I'm going to walk you through my thought process of when I approach a state pattern problem where I can't use control flow, but I need some changing behavior. So let's get into this jumper example. Hopefully you've all taken my advice from Monday and looked at the assignment. If you did rhyming dictionary, make sure you at least take a look at the assignment and the provided code for the physics engine. You don't have to understand the assignment itself and how to build the physics to understand the state pattern, but you should look at the way the jumping mechanic works in this game. And if you haven't, I'm still going to explain it here, but if you have, it's going to, what I go through probably will make more sense. Steal the assignment. Okay, let me slide this over a little bit. So today's lecture question, it is a lot of text. Hopefully you won't feel like it's a ton of work, but there's a lot of text that I have to communicate just to make sure we're on the same page in terms of naming everything and all the specific behavior. Whenever I'm not clear about the behavior that's expected, it just causes the entire class a lot of headaches, because if you don't understand what I'm trying to communicate to you, it's tough. So I used a lot of words here to make sure that I got this the behavior clearly defined. So for this, we're going to simulate the mechanics, the software for a TV, and specifically we're controlling the volume of the TV and whether it's on or off and whether it's muted related to the volume. So for this, of course, no control flow. We're using the state pattern again. And this one, I don't see any way you could possibly cheese this like you could on Monday without at least effectively implementing the state pattern. Maybe not through polymorphism and inheritance. You could do this with functional programming, but you'd still effectively be using the state pattern. So this one you're more forced into if you're one of the few people who cheesed the Monday lecture question. Hopefully nobody did or nobody will, but just in case, this one will catch up to you. So make this TV. The TV class is going to have an API with these 5 methods only: volume up, volume down, mute, power, current, volume, and also a test suite, test TV, that only calls these API methods. This is very important, just like all the other lecture questions, but more notably for these, because you're going to be writing a lot of classes of your own classes and your own methods and your own variables. You can't use any of those in the testing because they won't exist in my code when your tests are ran against my code. So we have to code through the interface, through this API. So in your testing, you can only create a new TV and call these 5 methods. The volume up, volume down, mute, and power are inputs. Those are like buttons you're hitting on the TV. And then current volume is your one way of testing. After these button presses, I expect the volume to be this, whatever it is, and then make sure that volume is what you expect it to be in your asserts. Assert current volume equals whatever I expect it to be. So what does this TV do? It starts off in the off state. I'll just say state. You know it's going to be a state named off. For the off status of this TV, I guess. The initial volume is 5. When the TV is off, the volume up, down, mute buttons, so these 3 methods do nothing. And if I call current volume, regardless of what the internal volume is, it's going to return, this current volume method is going to return 0 because the TV is not making any noise. The TV, the power button, the power method, this is going to turn the TV on and off. If the TV is on, it becomes off. If it's off, it becomes on. So you can see that as 2 states. You can see where the states are coming in here. The volume up button increases the volume by 1 up to a maximum of 10. The volume down button decreases the volume by 1 to a minimum of 0, which at first glance seems like it requires an if statement. I'll spoil this at the end of lecture if I have a quick minute, but I'll give you the quick way to do this without a conditional. Use either math min or math max. So if you increase the volume by 1, say volume equals volume plus 1, or math dot min volume plus 1 and 10. That way you can set it, you can have that maximum volume or minimum volume without using a conditional. So if you're wondering how to do that, there's your tip for that. Press the mute button, mutes the TV. When the TV is in the mute state, the current volume is always 0. But as soon as you hit one of the mute, volume up, or volume down buttons, any of these three buttons, the TV will unmute itself, return to the volume that it was at prior to being muted, but it won't increase or decrease the volume. So if I push volume up while the TV's muted, it will unmute but not increment the volume up, which is common behavior. I should mention, for this and microwave, I was playing with my appliances to see what the behavior, at least of mine, are. So some of these are modeled after the appliances that I just have in my house, just so you know. But I checked with some of the TAs and other students from previous semesters. They said theirs works pretty much the same way. I think most of these are pretty standard. And when turning the TV back on, the volume should return to where it was when the TV was initially off. So you can see that there's a volume variable. You're going to want a volume variable attached to this TV, independent of any of its states. And then in each state, the current volume is either going to return what that internal variable actually is, or 0, depending on that state. But then when we switch to another state, like if I turn the TV on, increment the volume twice, so the volume 7, and then turn the TV off, current volume is going to return 0 in the off state, but the TV still wants to remember this volume. So when I turn it back on, the volume is still 7, and I just resume using that variable. So if you have a volume variable inside the TV class itself, independent of state, then the state just controls, does current volume return that internal variable, that volume, or does it return 0? So you have a few states that return 0, a few states that return the volume. I guess just one state that returns the volume. But there's your lecture question with all the functionality. So we have a lot of specs. What we want to talk about today is how to take a set of specs like this and turn it into software. That's what we want to do today. So let's talk about the Jumper game. This is a 2D vertical scrolling platformer. I'm just going to replace that on my slides. Hey, there we go. Now I actually have the game right there. And the goal, the general rules of the game from the player perspective are pretty simple. I have 2 players. They can jump, they can move, they can climb, and as they climb, the screen is going to scroll up. Your goal is to climb faster than the other player. Once somebody reaches the bottom of the screen, they're gone. I can no longer control the red player. I can't jump. It's not that I'm just off the screen. That player's gone. So blue player won here, and if we were building this into a full game, it would say blue player wins, and then restart the game, etc. So this is what we want to build. And in a lot of the game, feel free to look through the code and see what it's all about, the structure of the code and everything. But really what we want to focus on today is the jumping mechanic of the Jumper game. It's named after the jumping mechanic because that is the most complex mechanic in this game. We've already seen how physics works in this game. These platforms... Oh, I'm on the wrong screen. No, I'm kind of on the right screen. These platforms extend static object, and when a player... Oh, I'm on the WAS. I'm on the West player. And when a player jumps up through the platform, they clip through it. But when they land on top of the platform, so when they have a collision with the top face of the platform, they stop. So we did that with physics. We talked about how to do that with polymorphism and inheritance. And then the player extends dynamic object. So as soon as I hit like the jump button, its velocity is being set. And then the physics engine takes over from there. So this has the completed homework in it and has all the physics from that assignment implemented in it. So on the physics engine side, we saw this. I don't want to dwell on it, but I don't want to skip over it either. So we saw the physics engine code, jumper object, extended static object, and platform and walls both extend jumper object. And I didn't mention, but the walls on the side here, got too many windows. I can't move through this wall. So I can't go off the edge of the screen to the left or right. And we did that through polymorphism. Or through inheritance and polymorphism. By having platforms and walls be jumper objects, overriding the collides with dynamic object, and then defining what happens when a dynamic object collides with one of these static objects, and it sets the velocity and location of those objects to what the values that they should be. So we're not allowing players to clip through the walls or fall through the platforms. And the player extends dynamic object, so all our physics works there as well. The player is going to set its intended velocity by hitting the inputs, the arrow keys and the jump key, and then the physics engine takes it from there. It says, okay, you're here are your dimensions, and here's where you want to have your velocity going. And then update location is going to say, here's your new location, and also remember your previous location. And then if there's a collision, you're not moving all the way into that intended location based on your intended velocity, and your velocity might be zeroed out. Your location might be changed on you by the physics engine through the collision detection of the physics engine. Okay, so now let's talk about, well, I guess it's the next slide. But let's talk about how that player actually moves around, the velocity set through the user inputs, and also the state of the player. And of course, this is what we want to talk about today, these states. That's all the good stuff. So there's only 3 buttons in this game: left button, right button, and jump. Player 1 is using A, D, and W. Player 2 is using left, right, and up arrows. So that's how I'm controlling both players at the same time during that game. Now let's talk about the good mechanics here. So the jumping behavior in this game, this is what we want to talk about today, and this is where we're going to get our spec sheet, all the expected behavior of the jumps, and how we're going to build this using the state pattern. So let's talk about each of these. And I want to control, so I'm going to have to do with I want to use the arrows, but I'll use last instead, I want to talk about each of these jump mechanics and talk about how this game works. So let's go through this spec sheet. When I push the left or right keys, I'm going to move left or right, pretty standard. I hit jump, and I'm going to jump, and I'm going to jump higher. Here's where we're starting to get into the more complex behaviors. I want to jump higher if I'm walking instead of standing still. So if I hold down the jump button, that's how high I can jump. If I'm walking first and do a running jump, I'm going to be able to jump higher. If I let go of the jump key early, I'm going to stunt my jump. So this is a full jump. I'm holding down the jump button the entire time. If I just tap the jump button, I'm going to jump lower. And if I hold it down a little bit longer, I can vary my jump height based on how long I hold the jump button. If I do a running jump, here's a running full jump. Here's a running tap jump. Here's a running kind of half mid jump. And then the strategy of the game becomes, when do you release the jump button? You want to just barely land on the platforms so you can jump right away again. A few of those jumps were pretty slow. Somebody's going to catch me there. There's a missed jump. But that's kind of the idea of the game, where the skill comes into the game. If I turn around midair, I should slow down. This one's a little hard to see, but when I turn around midair, I'm moving slower after I turn. So I can run and jump and get a full, nice momentum jump. But if I try to shift my momentum, slower when I turn around. I can jump through platforms while jumping up. We did this through physics. And land on platforms when falling down, again through physics. I'm going to fall if I walk off a ledge. And if I reach the bottom of the screen, as we saw with the red player, all my inputs are blocked and I can't do anything anymore. I already kind of showed off one of the spoilers, but we'll also want to add a double jump to this game. When I'm in the air, I get one extra jump, and then I don't get another jump. And also if I walk off a platform, I get my double jump. So I can walk off a platform and then jump back on. So there's all the mechanics of our game. That's what we want to build today. And we want to do that using some state pattern. I will warn you up front, I do use a few conditionals in this code. I'm not holding myself to the strict standard of no conditionals at all. But for the homework assignments and lecture questions, they're specifically designed so you don't run into any situations like that. But there are just a few situations in this game where I kind of needed a conditional, which makes this not suitable for a homework assignment, or else this could be a homework assignment. But I need a conditional. Primarily when I need to know when to transition from rising to falling, and I have to check if the apex of the jump was reached, if you're wondering about that. So we could do this without states. Certainly, we can do anything without states. But the code is going to get messy. My bet is if I gave you this as a homework assignment, if this was the spec sheet and I said, make this, do it however you want, a lot of the submissions are going to be really messy. You'll have these giant methods and just kind of a mess of code, a lot of conditionals, a lot of flags, and just a lot of different checks, and a lot of different behavior jammed into the same methods. MIT. This is at the University of Buffalo, UB. It is a college course, yes. So it'd be very hard to follow that code, but more importantly, it'd be hard to add new features. So with my spoiler, when we want to add the double jump, we're going to build according to this spec sheet. But when we want to add that double jump after we build all this functionality, if you're not using states and you have very disorganized code in general, it's going to be really hard to add that new feature, and you're probably going to have to retest all of your code. You're going to break existing features, etc. So we want to make things easy to expand, which is one of the themes of this course. We know how to write code. You can write this game. You can make this game based on that spec sheet. But how do we write it in a way that's going to help us add new features and maintain this code better when this game takes off and we got a decent user base, but they're like, you know what I really want? I want boulders falling from the top that are going to knock us down. How are we going to add that feature in an easy way? If we have a jumbled mess of code, that's going to be hard to do. If we have good organization and planning, then it's going to be a lot easier to be able to add those new features. So let's go through what I showed on the last slide of last time when I talked about how to design for the state pattern, and let's go through these steps that I suggested. So how to implement the state pattern. I like to do this in 3 separate steps. I like to do them in this order. Sometimes I'll switch up the order, but I had to pick something for the slides. First, write your API. Decide which methods are going to change behavior based on the state of the object that you're controlling. So of course the player here is the object that's going to apply the state pattern. The player is going to have a state object it contains, and then it's going to defer a lot of its functionality to the current state that it's in. So the API, what methods are we going to defer to the state for functionality? What do we want to say? Hey, state, this happened. What should I do? That's our API. So we want to decide what those methods are, and then each state defines what actually happens when those methods are called. The player just simply defers to the state for those API methods. So what's our API? What's changing behavior depending on state? And then which states should exist? Look for any situation where the set of behaviors defined by the API are different. And this is where I'll talk about that when we get to this point. So what states should this be in where the behavior is different, the set of behaviors? Even if one of these API methods should have different behavior, that's a new state. And finally, determine all the transitions between states. How do we move from one state to another? And what's the list of all of our transitions? So let's go through these 3 steps. API. The API is fairly simple in this one. It's whenever the player presses or releases a button. So the only inputs that we have to our player are pushing the left key, releasing the left key, pushing the right key, releasing the left key, pressing the jump key, releasing the jump key. And then also I use the 7th method for when the player lands on a platform, what should happen. That's a behavior that's going to change based on the state that we're in. So landing on a platform, walk off a ledge, that's going to be when left or right is pressed. Landing on a platform, right? Direction change, that's right or left was pressed or released. The jump button held, since we're checking if the jump button was held, how long it's held. I want to get when the jump button was pressed and also when it's released. So I want to check both of those events and then tell my current state, hey, the jump button was pressed. Hey, the jump button was released. And what should happen in each state. If the jump button's released when I'm jumping up in the air, that should have different behavior than if the jump button's released after I land on the ground or as I'm falling back down. That should have no behavior if I'm falling down or if I'm standing on a platform. But if I release the jump button as I'm jumping up, then that should have the behavior of dampening my jump. when jump is pressed, keys are pressed. So we can pick out these keywords from the spec sheet. You can do that for today's lecture question, Friday's lecture question. Go through the spec sheet and what are those actions that are happening that need different behavior depending on the state. What state should we have? So now we're kind of looking at the action, or I guess not the actions, but we're looking through this and figuring out what those states are. We can either be walking, jumping, standing, in the air. We can be in the air rising up, in the air falling down, and we can be on the bottom of the screen. So I'm looking through my spec sheet and I'm picking out all those states, writing down all those states and deciding, okay, these are the conditions I can be in where the API methods are going to have different behaviors. So I'm, again, looking through my spec sheet and picking all those things out. So I have my list of methods, I have my list of states, and these might change as your design changes. Of course, this one isn't going to change because I already have the code written. But as I was writing the code, I did change around my states and my API. Like I didn't realize at first that I needed this land on platform method. But I added that as I was writing the code and revised this. So I have my API, I have my states, and for each state, we're going to have to implement each API method. When I'm standing still and I release the left arrow button, what should happen? When I'm rising up and I release the jump button, what should happen? If I'm rising up and I hit the jump button, press the jump button again, what should happen? Etc. Yeah, Scala compiles into Java bytecode, so it compiles into the same language that Java compiles to, and it can run on the JVM. And finally, our last step is deciding what the state transitions are. And of course, when we go to write the code, I already said that, but when we go to write the code, we'll create a class for each one of those states, an abstract class for all of the API methods, and each state is going to extend that and then implement each method. So when we go to writing the code using the state paradigm, the code should be pretty easy to write. Going through, like I said on the last slide, for each one of these states, what should each one of these API methods do? And each one of those methods should be pretty easy to write. The state pattern is a big trade-off between designing the structure of your program, and writing your actual code. Your code gets a lot easier, but the design gets a lot tougher. So it's kind of a different way of thinking. It's going to be a different way of approaching writing code than you might be used to. So finally, we're going to look at the state transitions. Again, we go through our spec sheet and look for each event that can happen that's going to change the state of the player. So walk left and right when keys are pressed. If I'm in the standing state and right or left is pressed, I'm going to enter the walking state. If I'm walking and I release left or right, we're not going to have momentum when we're walking. That's not on our spec sheet. We're just going to stop immediately and be in the standing still state. If we're walking, standing, and jump is pressed, we're going to transition to the jumping state. If we're in the falling state and we land on a platform, we're going to transition into the standing state. And then if we're, I forgot how exactly I implement that, did I? Standing. And then I think I check if left or right was pressed and not released. We're going to immediately transition into the walking phase. And then walking, if you walk off a ledge, you're going to transition to the falling state. And from any state, how did I miss that? My brain just completely skipped this one. If you're jumping and you reach the apex of your jump, this is the one case where I couldn't see any way to avoid a conditional. But I need to have different behavior whether I'm jumping up or falling down. I need different behavior for both of those. And that state transition happens at the apex of the jump. So I check if my z velocity is negative and I'm in the jumping state, I'm going to transition into the falling state because I've reached the apex of my jump. And then no matter what state you're in, you reach the bottom of the screen, you're done. I don't care if you're jumping up, falling down, standing, walking. I don't care. You reach the bottom of the screen, you're done. So, given all that, it's a lot of information that we've dissected from the spec sheet. So let's visualize this like we saw last time using a state diagram. So I want a state diagram which is going to show me all the states that I can be in I have my 5 states here: rising, falling, standing, walking, game over. And I want to visualize all the state transitions between them. This is going to be a lot easier than looking through code and trying to look at all these classes and figuring out what they do and trying to go, okay, if I'm in this state and this method was called, I go to this state, switch to that file, and then if this happens, I go to this state, switch to that file. The state diagram gives us a much better view of the structure of the code. So this can be part of the documentation that accompanies your code that makes it easier for new developers to join the team. Of course, not in this class, but out there in the real world or side project you're working on with your friends. You have a state diagram, and everybody can follow what's going on with the overall structure of the code. Now, you might have to go into the code for each class to figure out how each API method is implemented for each class. But this is going to give us all the states and all the state transitions in one nice picture. It's going to tell us how this game works. So if I'm standing still, left or right is pressed, I go to walking, released, go back to standing. To hit the jump button from walking or standing, go into the rising state. Reach the apex of my jump, go to falling, land on a platform, go to standing, walk off a platform, go to falling, and reach the bottom no matter what state we're in. I didn't want to draw 4 arrows and mess up all the imagery here, but any state, reach the bottom of the screen, donezo. Views count below 100. I know it's sad. For those not in the course, there are 229 students enrolled. So the view count's sad, but to be fair, some of them do have just scheduling conflicts, so they watch the VODs after. I upload all the videos to YouTube, or rather my TA does. And hopefully, I mean, my optimistic side says the rest of the class is watching the VODs. Some students like to watch things at 2 times speed. I get it. But the view counts don't quite reflect that either sometimes. But the view counts are decent if you assume that they're all unique viewers, but people rewatch the lectures too. It is what it is. Online learning's tough. It's tough to stay motivated and keep on track. I mean, you got to do it though, but I understand that it's tough. But at the end of the day, I have to grade you on your performance, so keep that in mind. You're here for me. I mean, for me personally, if I'm lecturing to one person, I don't, it is what it is. But I mean, you're paying for me to teach you. That's the part I never understand. You're paying tens of thousands of dollars over years, several years, for me and my colleagues to teach you stuff. The least you could do, for whoever's paying your tuition bills is to, show up. But I mean, if you want to pay my salary and then not make me work for it, from my personal standpoint, now I would much rather see my students be successful. But from my personal standpoint, it doesn't really affect me. It makes me sad because, what am I doing this for when a lot of the class stops? But, we still have, 96? I'm still doing it for 96 of you, so I'm happy in that respect. But anyway, we're not here to talk about that. So we have our state diagram, and now once we have this state diagram, it would be a matter of creating a class for each one of these states and implementing those API methods for the behavior expected in each one of these states, including the state transitions. If I'm in the standing state, my left or right key pressed methods better include, it can have some other logic, but it better also include a transition into the walking state. So now it's easier to refer to this diagram, and for the homework especially, sit down and write this diagram out. Here's where I want to say what I was almost said a few slides ago, is when you're writing the state patterns, like for the lecture questions, the states in the state diagram, it's going to be pretty easy to generate because the questions themselves aren't too complicated. When you get to the microwave and the calculator homework assignments, though, these state patterns get a bit trickier, and it's not immediately clear even like how many states you should have or what those states should be. There is a lot more design involved in those homework assignments. So one of the things that I want to recommend, and for my solution for each of those, I spent a lot of time with just pen and paper, drawing out state diagrams and then redrawing them when I realized they were crap and they weren't going to work, redrawing them until I had the states for all the different sets of expected behavior. And I sat there with my desktop calculator open, clicking buttons and drawing out my states and redrawing them based on the behavior. And the assignment is based on the common functionality of pretty much any 4-function calculator, by the way. So you can use your desktop calculator. In most cases, it's going to do the same thing that we expect. So anyway, when you are drawing those state diagrams, especially the more complex ones for the homework assignments, you should understand each time you're going to be in some initial state, go through the API, figure out what each button is going to do, and then after each button press from the initial state, think about what all the buttons are going to do now. So I'm in the initial state and I hit the button 5, for example. What should all of the buttons do now? What if I hit the plus button? What if I hit the equals button? I think both of those are undefined from the initial state. But what if I hit the decimal button? What if I hit 5 and then plus? What do all the buttons do now? And each time you ask that question, ask yourself, is this a new state? Is this identical to some state that I've already created? Is all of the functionality exactly the same? Then I'm in this state still. If it's different, I have a state transition. And then as you build out your state diagram, as you have more and more states, make sure you're always asking, am I transitioning into a state that already exists? Once you start transitioning into states that already exist, that's when your design starts to come to an end. So you have enough states that you don't have any situation you can get yourself in where you have the same exact behavior as you did before, or where you have different behavior from a state that you already have existing. So you might hit 5, 4, plus 8 equals plus 3, like somewhere in there you're going to duplicate a complete set of behavior from the API. That means you can start folding the state diagram in on itself and just transitioning back into another state. Like when I went to standing, when jump is pressed, I know I have a different set of behavior. When I hit the apex, I know I have a different set of behavior. But once I land on the platform, I'm not creating another state for that, because I'm realizing that if I fell and landed on a platform, I have the same exact set of behavior that I do when I'm in the standing state. So instead of creating another state for that, because the behavior did change, I'm realizing that, oh, that's the same exact behavior as I have in the standing state. So I'm going to transition back to that and start closing this diagram in on itself and maxing out at 5 states instead of creating new states. So that's my tip for when you're designing for those homeworks, designing your state diagram. And again, I would highly recommend starting with pen, paper, or whiteboard, or however you want to think, just not in code, and write out these state diagrams that you're going to have. If we hit a button, the program crashes. It's not the best spec sheet for a program, but hey, go for it. It'd be easy to code. If you submit your code, your homework in assembly, you might not get any points. Or you might get all the points. Hell, I might just be that impressed. If you can do, this is object-oriented programming, so if you can do OOP in assembly, I would probably be so impressed that I would just, I would give it to you. With no branching in assembly, I think you'd have to use conditionals. You'd have to use jumps. So this is there are a lot of classes. We have 5 classes here. And what we can notice is that walking and standing are going to have a lot of the same behavior. We're on the ground. And falling and rising have a lot of the same behavior, where both of those are in the air. So I'm going to take that fact and notice, I want to try to emphasize the difference between giving degrees to students at other schools. Yeah, I'll send anybody a degree. It might not mean anything, but I'll just write degree on a piece of paper. I'll write it in crayon too and then sign it. Ship it to you. So, I want to emphasize the difference between inheritance and polymorphism. Last semester there was a lot of confusion with this, so I'm trying to emphasize it a bit more this semester. So this is all using polymorphism. It is using inheritance as well. But let me explain the difference. We're going to have an abstract state class that defines the API. And then we're going to extend that class in these 5 classes using inheritance. So creating these classes, that's using inheritance. These classes are going to inherit from the abstract state class. and get all the functionality from that class, which is the definition of the API. What methods do we need to implement is what they're inheriting from another class. When we create the player class, the player is going to have a variable of type state, and that variable can store objects of any of these 5 types in it. Since these variables, objects of these types can be stored in, we're storing them in a variable of a different type, the I'll just click through the next slide. In the state type, variables of these types, objects of these types can be stored in a variable of the state type. That's what the player is going to do. It's going to have one variable of type state, and that state can store objects of either game over, falling, rising, walking, or standing. And depending on what type is actually stored in that variable, that's going to change the behavior. So that's when we're using polymorphism. We're taking objects of one type and storing them in variables of another type up its type hierarchy. So rising extends in air, extends state, and I'll explain in air and on ground in a second. Rising extends in air, extends state through inheritance, and then once we store an object of type rising in a variable of type state, that's polymorphism. So we have one variable of type state, and it can actually be any of these 5 types through polymorphism. These types are pretending to be different types. A review session every Wednesday. I think it's 5. It might be 3 or 4. I don't know. Check the course website though. So here we can notice what I said before. Rising and falling have a lot of shared functionality, and walking and standing are going to have a lot of shared functionality. So we can factor out that functionality and leverage our inheritance a little more, like we did when we first talked about inheritance last Monday, is take all the common functionality between these, remove all that duplicated code, and put it in a shared class that has only the shared functionality. And this will be another abstract class. We can't actually be in the on-ground state, but this will have all the functionality that should occur if we're on the ground. And then walking and standing will extend on ground and implement anything that's left over, anything that's different between walking and standing. These classes are going to implement that functionality. Same for in air. Anything that is true for being in the air regardless of state, that's going in the in air abstract class. And then rising and falling are both going to extend in air and only implement the things that are different between falling and rising. And everything that's common between them goes in the in air class. And game over just extends state directly. So this is our new inheritance tree, the state class. This is the only thing the player class cares about. It has one variable of type state, and then that state can be any of these things in this type hierarchy. I don't know if they record the review sessions, but they do stream on Twitch, so you will have the Twitch VOD for however long Twitch stores them until they delete. I forget how long Twitch stores the VODs, but you will have the Twitch VODs at the very least. They do record them. Cool. 2 weeks Twitch and it depends on if you pay for Twitch or not. There's a different time frame. I forget what the 2 time frames are. I think 2 weeks is if you don't pay, and I believe it's like a month and a half if you do. But 2 weeks, and then if they record them too, all the better. There you go. They said they put them on YouTube. Perfect. So, any questions up until this point? This is the one thing, like using Twitch, I just watch the chat, so if you have questions, you can ask at any time. One kind of disadvantage of that is I stopping the lecture and asking for questions, which can be a good time to digest all the things that I've talked about. We don't really have those slowdowns anymore, so let me try to get one in here. Everyone good up until this point? Yeah, I can't see all the blank stares. Believe me, I'm picturing the blank stares. Like, oh man, they're not going to get all this right away. Most of these lectures, I would guess that you have to rewatch them at least once to fully get what's going on. I think most CS lectures, you can follow a lecture decently well, but once it comes time to take the content of that lecture and apply it to solve a programming problem that you have to solve, take that concept from lecture and apply it to writing code, that's where it gets a lot tougher. That's where you usually have to rewatch at least once. Which at least everything's recorded now that you can rewatch it. When it's an IRL lecture not recorded, it's a lot tougher. Can an abstract class extend another abstract class? Sure can. I did it right here. In air and state are both... I think I actually made them... They could be concrete classes, just the way I implemented it. We'll go to the code. We have a few minutes here. We only have 5 minutes. But these can both be abstract classes. Yep. But I can't, since this is an abstract class, I still can't say new in air or new state because they're abstract. I can only say new standing, walking, rising, falling, game over. Does P equal NP? I lean towards no on the P versus NP, but it's a tough one. Time to draw. Good call. Rewatch for every lecture question. Good call there, too. And that's why I can't trust the view counters on the videos, on the VODs. Because if everybody who watches the lecture is also rewatching, that's going to skew the view count. Yeah, exactly. Probably the same people watching multiple times. Just testing, understood the lecture. Reference testing. Yeah, that's not about today's lecture, but I can talk about that after today's lecture ends. The best approach, a bunch of debugger. I want to run the debugger more. I always plan to, but then my lectures always fill up. You know, I can't get to running examples. Speaking of, let's keep this moving. So, as I spoiled earlier, how do we add a double jump to this game? If we wrote all that without the state pattern, it might be a little tough. But let's look at the design of adding a double jump. So for the double jump, we can jump one more time while we're in the air, including walking off a platform. I can still use up my double jump. I don't have to jump and then jump again. I can walk off and then use my one double jump, but I can't jump twice after walking off a platform. With poor design, that's going to be tough. We're going to have to retest a lot of code. We're probably going to break existing features. It's just going to be a bad time. With our state pattern, not really a problem at all. So with our state pattern, if we're rising or falling in either of those two states and the jump button is pressed, we're going to set the z velocity to the jump velocity. So in rising and falling, if you jump, you get to jump again. And that's kind of it. A little bit more though. Now after we jump, when we're in the rising and falling state, our set of functionality from all the API methods did change, because now we can't jump another time. We can't just continuously jump. So if we're in rising and we jump, we can't stay in the rising state, because then we could just jump infinitely while we're in the air, and then the game's not very fun. So we're going to add a few more states, rising after double jump and falling after double jump. They both just extend rising and falling respectively, except they override the jump button to do nothing. So it just says override, jump pressed, open brace, close brace. That's all these classes are. Same thing as the rising and falling states, just disabling the double jump. And then we have one extra piece of functionality when we reach the apex after a rising, while we're in the rising after double jump. We don't want to transition into falling, so we do have to override the apex reached method as well to be falling after double jump, which I didn't really mention the apex reached method, didn't I? Did I? The falling method, actually. That should probably be in the API. So, arguably, you could do this. This might even be the best approach for this particular case, is to have a flag use double jump false. If I didn't use the double jump, let the player use the double jump, because we did have to add 2 extra states to implement this double jump. So this one is very debatable, and I'd probably even lean towards this being a better solution. It's a little cleaner. It avoids creating 2 new classes. It keeps the directory complexity down a little bit, even though we have to use a flag here. So you could use this state, but more to the point, what if you just can't? What if your professor says no control flow for the assignments? That's the real situation that you're in right now. So we want to be creative in the ways that we solve these problems. We don't want to do what you would do in 115 and use this flag. This is how you would code it without knowing about the state pattern. Now, knowing the state pattern, let's get a little more creative and explore the state pattern a little further. And even more to the point, calculator, the decimal button should only work the first time you press it, and after that it does nothing. And this lecture, this double jump part of the lecture, is specifically designed to say, hey, this is how you're going to do that decimal functionality. It's the problem. Yeah, do it small. This is for you right here. Double jump. Review that code in the jumper handout. Oh my goodness, we're at 240 already. I didn't even get to the code. So our state pattern gets a little more complex. This is where I would say, one if statement, use that conditional in the rising and falling, or rather in the in-air state, to avoid this complexity. But if we're committing to the state pattern, we have these 2 extra states, a few more transitions, and we can build this by having just these 2 extra classes. And then we have a little bit of extra information on our inheritance tree. And yeah, I guess this is another one that I haven't mentioned explicitly, but you can extend a concrete class. So falling and rising, those are already full concrete classes. They're not abstract. And we can still extend those as well, just to override some of their functionality. And we're back to the lecture question. This is one time where I will show the bonus slide. Just because this math.min and max can be tricky if you just don't know what to do here. The math.max and min. So you have to have some max volume and min volume 10 and 0. And we need to do that without conditionals. You would want to write something if volume equals 10 and volume up was pressed, don't do anything else, increment it by 1. You'd like to do something like that, but we can't use that conditional. You can get around that by using math.max and math.min. So for example, if we're decrementing the volume, let's say the volume's 5 in its initial state, and we hit volume down, instead of saying volume equals volume minus 1, to handle this min volume, we can say volume equals math.max of 0 and volume minus 1. So if volume is 5, this is going to be 4. Max of 0 and 4 is 4. Cool. Decrement again. 3, cool. 2, cool. 1, cool. 0, cool. Now when the volume is currently 0, this is going to be negative 1. Math.max is going to say 0 is greater than negative 1. And it's going to return 0. And it's going to give you that bottoming out functionality, that min of 0, by taking the max without writing a conditional. So we don't actually care what the return value is here, but depending on what is, what these values are, it's either going to be this one or this one. So we're kind of simulating a conditional. There is a conditional somewhere in that max method that we are taking advantage of, but if it's not in your code, I'm going to call it okay. As long as you're not simulating a conditional in your assignments, as long as you're not running code that you've written conditionally, I'm going to be fine with that. So you can kind of simulate some conditionals here by using some built-in methods. And same with min, math.min of 10 and volume plus 1 is going to get you the same thing. Right, I'm sad I didn't get to the code, so I'll do a little bit of it here during the chat. And that's officially the end of the lecture. But I'm not going to find any other... Not going to find any other time to talk about this, so to visit the code. So I want to do it now. That's why it was resized different. Oh, there we go. We're on track now. Okay, so let's take a look at the actual code for that to really get a good grasp on what we just saw. So a lot of the implementation is 115 level coding. Once you have everything set up in the design, you should be able to know what to code. But some of the things are still maybe a little fuzzy there. So I do want to show some code, but there's nothing too complex or too crazy here. Most of it is setting up the state pattern, and that's why today's lecture I didn't really show any code about the state pattern at all. Just the code reminding you of how we did the physics and some of the inheritance. But I do want to show that code still, at least here for a few minutes, even if didn't make it into lecture proper. So here's the player class extends dynamic object, has one variable of type player state, and we're going to start in the standing state and then pass a reference to the player to which it's attached to. to be able to, so the state can update itself, can change the state, and can access the variables inside the player class. In the player, I'm going to define all these variables. If you really want to play around with the game and you have your physics engine complete, play around with these variables and get some fun, different behavior. I played around with the game just in testing. I did a bunch of play testing and got values that I feel good for the game. But if you want to, have the player be able to jump like crazy, play around with it and see what everything changes. Then I have a little bit of extra code. I want to know if each key is held down. I want to be able to always ask, is this key currently down? So I have a little bit of bookkeeping. When left is pressed, for example, I'm going to set held to true, and then when it's released, I'm going to set that to false. So now I can always ask, is this key down at this current point in time? And that's how when I land on a platform, I'm going to go to the standing state and then immediately transition into the walking state because I'm going to check, is that key held down? If it's held down, transition to that state. But all the methods, like I said, and update, I don't think I'm even using. I wanted that for to be able to tell how much time has passed, how long I've been in a current state. That's something I would use if I was going to have a speed run, which I was initially going to add. If you're walking in one direction for long enough, you'll pick up even more speed and be able to jump even higher. But I didn't end up using that one. On ground and is alive is a method that I added just so the game and the GUI can track if a player is alive or not. I just display a quick message that says this player died on the console. All right, the states, what we came here for. So the player state, again, this time and state I didn't end up using. This line I use just to show all the transitions. If you have your physics engine done and you're playing the game, you'll notice in the console, actually we should be able to, we can see it, it'll print out every time a state changes, it'll print out what state you just changed into. So you can actually see these states transitioning as you're playing the game. So I just added that print line just to be able to visualize that, and it helped with debugging as well. Sometimes print line debugging, it does help sometimes in certain situations. I wouldn't want to set a breakpoint here and then look through all the variables every single time. I want to play the game and just watch the states transitioning. And if velocity less than z, I'm going to call that falling method so I can transition, hit the apex of the jump. And I'm going to define the methods. So I did I do this? Yeah, I didn't even do this as abstract. This should probably be abstract. I don't know why I didn't. Even though it can be a concrete class, because I did have default implementations for this. Every API method, I default to doing nothing. And then when I extend this class, I'm only going to override the methods that actually do something. So by default, everything does nothing. So if I don't override a method, it just continues to do nothing. And then left release and right release, this always stops the player. So I'm going to call the player stop method in either of those cases. On ground is going to have some of that functionality. If left or right is pressed, we're going to start walking. And we're going to have the player walk left, which I didn't mention these. I have some utility methods in the player class, which are going to set their player's velocity to certain values depending on the current situation. And then all the states can call these methods to simplify the logic in each state. I don't want to duplicate this code in each state that can walk or move or stop. No, collide with dynamic object. I don't want to talk about that one. So this is common for standing or walking. In standing, jump is going to do something different than if you're walking, specifically the velocity that you're going to jump with. And you do the jumping just by setting the z velocity to whatever velocity a jump should be. So you hit the jump button, your velocity is set to the jump velocity, and then you carry that velocity by leveraging the physics engine by being a dynamic object. Same thing here, but I have my walking jump velocity, so that's how I'm jumping higher if I'm walking as opposed to standing. And then a few extra methods, transitioning back into the standing state. Oh, yeah. Yeah, and left is press. I don't do a state transition. There's the difference. I think I did that just so I don't print walking, 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 walking. Or whatever I'm walking. Or would it do that? It doesn't matter. In air, if left or right is pressed, I'm going to transition. So even if you hold left through your jump, release left, and then hit left, it's going to count that as changing direction in midair. When jump is pressed, we're going to hit our double jump velocity, which I set as the standing jump velocity, not the walking jump velocity. So you get a small jump as your double jump, and then transition to rising after double jump, which just zeroes out, blanks out the jump button. And if you start falling, you're going to fall after the double jump instead of going into the falling state like we do here. Then falling, if you hit a platform, you're going to transition to standing. Falling after a double jump, just blank out the jump button. So every method here, and rising, I forgot this one. If you release the jump button while you're rising, the way to get different jump heights for how long you've pressed and held the jump button, I did that by when you release jump, when you're rising, cut your Z velocity in half. And that's it. That's how I got that behavior. Easy peasy. So when you notice, when I'm going through these states, yes, there are a lot of states and a lot of classes here, but each method that's implemented is really straightforward. When you're saying, if I'm standing and I press the jump button, what should happen? Well, I want to get some Z velocity, and I'm going to transition to the rising state. So every one of these methods is 1 or 2 lines long. Each method is very simple to write, but you're trading this off by having to design a lot more. Once you have the design and the state diagram, actually writing the code, it's just a matter of creating a class for each state and then implementing the behavior for each method in each state. So actually writing the code gets a lot easier and a lot simpler. But, in the game over class, I just blank out every single method. A lot of these, they're already blanked out from the state class, so I didn't have to do all of them, but I don't know. I wanted to because it really emphasizes the point that you can't do anything when you're in the game over state. Oh, and transitioning to the game over state. Where did I put that right in the player? It won't be in the game. Huh. I wouldn't have put that in the game. I should refactor this if I did. It's silly. I did. Huh. Check if player fell. That should call a method in the player. That shouldn't change player state directly. If you're here for 442 and you're here a little early, just disregard this because I've been telling you how bad stuff like that is over the past few lectures. That's something I shouldn't be doing. I should call player dot reach bottom of the screen, and then the player class should control its change of state. I shouldn't have a separate class changing the state of the player like that. Player needs to control its own state. That's a bad thing. That's a do what I say, not as I do moment right there. So that's the code. That's how the jumper game's implemented. Let's since I changed that jump velocity, let's run this once. I don't have it in focus. Woo, yeah. It's the walking jump velocity. Yeah, I did. That's a full jump. Oh, and let's double jump. So the standing jump velocity I didn't change. But once I'm walking, woo, that walking jump velocity. First one to jump wins. As long as they're not standing still, though. Yeah, you be Marcos. I was shocked how many. So looking through the the auto lab results for the first homework, I was shocked how many students were attempting the homework who only had like one or two lecture questions done. The course, like I put a lot of thought into the design of this course. The lecture questions are made to ease you into the homework, as you're mentioning. And I'm just shocked how many students don't do that. They just wait for a deadline to occur, and that's when they're going to do the work. And since the lecture questions aren't due until the end of the semester, they're not doing them. But when the homework deadline came up, they tried to bang their heads against the homework without learning what they were supposed to learn in the lecture questions. And especially with this homework 2, these last 3 lecture questions, 2.4, 2.5, and 2.6, are obviously being related to the state pattern, are directly helping you with the homework in a very, very real way, much more so than with homework 1. So if you have that strategy and you're trying to do the same thing on homework 2 as homework 1, if you're trying to not do the lecture questions or just do the first couple and then jam yourself into the homework, you're just setting yourself up for failure. Do the lecture questions as we're going over the lectures. Don't wait 5 weeks, a few weeks later to do them, or a few days later even. Do those lecture questions as you're watching the lectures on time, and you're going to win the course. Don't do that. It's a quick way to failure. Or at least not getting the grade you want, because those homework deadlines pass, and then you didn't do enough to get an extension, but then you make up the lecture questions and make everything up towards the end of the semester. You can't get those homeworks back. You can still pass, but you ain't getting those homeworks back. Yeah, for the homework, you should make separate classes for each state. And for the lecture question, too. It's kind of what I'm saying. If you do today's lecture question and Monday's lecture question, you'll see exactly what I mean by that. Creating a state abstract class and then extending that in all your concrete states. You'll get a good feel for how that works. And you should get a better understanding of inheritance and polymorphism. You're creating all these other concrete states using inheritance, and then you're applying polymorphism to have the object that has the state be able to change its behavior depending on the type that's stored in that variable of type state, what actual class it is. So the player has one variable of type player state, and that state variable can store an object of either falling, rising, etc. And depending on what type is actually stored in that variable, it's going to change the behavior of the player object. Lecture questions says functionality did not pass all tests. I didn't have any conditionals. I mean, how were the testing? Did you have all the testing good? Didn't pass all my tests, but that's only half of it. Were your tests good? Didn't pass all tests means I ran my test suite against your code, and at least one of my asserts failed on your code. So if you do your own thorough testing, as long as your testing is as thorough as mine, you won't have that problem. But I don't share any information about the functionality about my tests, because a big part of this course is you got to learn how to test your own code. So I need you testing all of the functionality. Everything that... I don't need jumper on here anymore. Anything that shows up on this sheet, you need to have tested and run your tests against your own code. Then you won't have to submit to Autolab. You shouldn't be submitting to Autolab more than a handful of times in this course. You should be writing your own tests and then running your code. Make sure you test every piece of functionality that's shown here, and then you're going to be fine. You're going to be doing well. The only time you need to submit to Autolab a bunch of times is if you have just some incompatibility with Autolab. You have errors during your tests. Maybe you have something named wrong. It just takes you a few submissions to figure out. Or maybe you have that one test case that you just can't figure out. One of my incorrect solutions is really eluding you. But again, if you're testing all the stated functionality in your unit testing, that shouldn't be an issue either.